Hello, folks. I just wanted to go through the notes from week 2 and cover a few things from week 1 in a little more depth as we go. So this is part of Unit 9, our thermodynamics unit. And last week we talked about states of matter and phase changes. So just to quickly go through those, our solids, our molecules are close together. We have a definite volume and a definite shape, cannot be compressed, cannot flow, and is the lowest energy of the three states that we've discussed. Liquids, molecules are close together, but not as close as a solid. One exception there being ice particles. Remember, ice is less dense than water. But liquids have a definite volume. They do not have a definite shape. They cannot be compressed. They can flow and move, and they are the middle energy state. Our gases is where our molecules are most spread apart. They do not have a definite volume. They do take the shape of the container. They can be compressed, they can flow and move readily, and they are the highest energy of the three states that we discuss. We've talked about phase changes last week, that we have 6 phase changes, depending on are we adding energy into the system or are we taking energy away from the system. And the deposition and sublimation pieces are the ones that we typically have to change with pressure in order to see that transition. So how do temperature and pressure changes affect states of matter? We can change that temperature and pressure using our knowledge of ionic and molecular compounds to change the state of matter a substance is in. So what happens to temperature when ice melts? What happens to temperature as water is heated and then as water boils? There is a video on making a heating curve on our Google Classroom if you would like to take a look at it. All right, so our heating curve, we have these distinct positive slopes and plateaus. So whenever we have that plateau, that is our phase change, and that is a physical change. And at that time, temperature does not change. When we have our positive slopes, that is when we are heating the liquid or heating the solid or the gas, and we are seeing that temperature change. Okay. So this really plays into the laws of thermodynamics. And our first law of thermodynamics is the law of conservation of energy. Energy can be neither created nor destroyed, but can be converted from one form to another. And energy in the universe is constant. So if the temperature does not increase during a phase change, where does the energy go? That is what we will continue to review today. So we have our 2 types of energy. We have our kinetic energy and our potential energy. Kinetic energy is due to motion and depends on the mass of an object and its velocity. Depends on the mass of the object and its velocity. So there's that physics equation there, Ke equals 1/2 mv squared. And our temperature then is the average kinetic energy of our system. Potential energy is due to position or composition and can be converted into work. So the more bonds you have, the bigger source of energy. So in all these cases, the more mass you have, the more potential or kinetic energy you can have, which is in part why something like the ocean takes a very long time to heat up, while a glass of water can become room temperature very quickly when the ice melts. So again, to review from last week, we have our potential and kinetic energy. Our potential energy increases during those phase changes. And that is going to end up being where we are breaking our intermolecular forces. And once those bonds have broken and our states of matter are exposed to heat, that kinetic energy can then go to increasing, those molecules will move around faster, and that kinetic energy will increase. All right. So remember, for our intermolecular forces, solids have stronger intermolecular forces than liquids, which have stronger intermolecular forces than gases. So when you change from a solid to a liquid or from a liquid to a gas, you overcome or break those intermolecular forces. And that's why temperature doesn't change during a phase change. The energy from the heat is going to breaking apart those intermolecular forces. And just a quick review on our IMFs. Remember, intermolecular forces are keeping different molecules attracted to one another. So when these phase changes are occurring, the energy is actually being used to pull those molecules apart from one another and disrupt those attractive forces. So for covalent molecules that have LDFs, dipole-dipole, or hydrogen bonding, that means overcoming relatively weak forces. And remember that you are not breaking apart the covalent bonds inside each molecule. When you heat liquid water and create steam, you're making water vapor. You are not breaking it down into hydrogen and oxygen gas. Our IMFs, so for ionic compounds, there's something called Coulombic attraction. That term popped up, I think, on a POGL we had back at the beginning of the year. But basically, these electrostatic attractions between these ions hold true and keep them attracted even as we're adding energy and even as those ions are spreading further apart. And so we have these delocalized electrons, we have this Coulombic attraction, and that means that we need a lot of energy in order to pull those ions apart. So it requires far more energy to melt an ionic compound. And that's what we saw in a lab back earlier this year. If you remember, we put 4 powders onto a hot plate and 2 of them melted and 2 of them did not. The 2 that melted were types of sugar that had covalent bonds, and the 2 that did not melt were types of salts that had ionic bonds. And the energy of the hot plate was not enough to overcome those Coulombic attractions that we could see in our ionic compound. One thing to think about is that covalent network solids, like a diamond, these do not have distinct molecules like water does. It's a network of covalent bonds. So to melt it, you do have to break those bonds. So breaking those covalent bonds does take far more energy than just disrupting something like LDFs or a hydrogen bond. So on the pictures here, you can see things like diamond, which is just a network of carbon. You can also see graphite on the other side. That is also just a network of carbon arranged differently. In the middle, silicon dioxide, silicon carbide, just showing you some other arrangements of these molecules. So silicon dioxide is a component of glass. So when you take that silicon dioxide and you do things like add heat and vitrify it like you would in a kiln for ceramics, you turn it into this network of glass that really changes the composition of that material and creates those covalent networks. And that is going to increase the melting point of that substance. This is a similar slide from last week. At standard pressure, you don't typically see sublimation and deposition. So we can change both temperature and pressure in order to see all those phase changes. So we have our phase change diagram. We have our triple point. So we have our triple point, and that is the temperature at which all 3 states of matter exist at equilibrium. We have our critical point up here, And that is where our two phases become indistinguishable from another. Remember, the high heat wants to evaporate all liquids, but the high pressure wants to condense a gas back into a liquid. And so we get that supercritical fluid that we cannot take apart. Our phase diagrams, comparing something like carbon dioxide and water, at 1 atmosphere of pressure, CO2 will sublime. And so that would be our example of dry ice. If you wanted liquid carbon dioxide, you would have to raise the pressure quite high, especially if you were keeping it at room temperature. For water, we can see things like our 0 degrees Celsius melting point and our 100 degrees Celsius boiling point, and this kind of unusual slope between B and A, that we have a negative slope. And remember that ice is less dense than water. And as you increase the pressure, then the melting point of water decreases. And in all these cases, if you add or take away heat, add or take away pressure, you can make different conditions in order to get those different states of matter. Okay, heat exchange. So this gets us fully into the new material from this week. And we'll start with temperature versus heat. So temperature reflects the random motion of particles. Remember, temperature and heat are related to our kinetic energy. Temperature is that average kinetic energy. So heat involves the transfer of energy between two objects due to a temperature difference. So at constant pressure, the change in enthalpy, also known as delta H, is equal to the energy flow as heat. So if you recall, when we had looked at potential energy diagrams, we had drawn some pictures that had this curve in it. So we'd have the heat of our reactants and our products. And depending on that relationship, delta H could be positive or negative. So what I have drawn here was an exothermic reaction, which would have a negative delta H. And that would mean that energy is leaving the system. And so this would be something that would feel warm. And just to clarify systems and surroundings, so our system is what we're focusing our attention on. So that would be the reactants and the products of a reaction. The surroundings is everything else in the universe. Put them together, systems and surroundings, and we get our universe. So with our heat exchange, remember we can have an endothermic reaction where heat is absorbed. So that is a positive delta H. That means that the reactants have less energy than the products. Heat flows into the system from the surroundings, and it would therefore feel cold. So that would be an instant ice pack, for example, when it is triggered. An exothermic reaction, heat is produced. So we have a negative delta H at constant pressure. Heat will flow out of the system and into the surroundings, and it will therefore feel hot. And the energy gained by the surroundings is equal to the energy lost by the system. All right, so with thermodynamics, we've talked about a lot of the qualitative things that we need to discuss. But because we're talking about energy, all of these things can be done with our calculations. And we have two main types of calculations that we need to look at. So if we're looking at our heating curve, we have two types of energy dependent physical changes for each substance. So that is our freezing and melting versus our condensing and vaporizing. And those phase changes are going to constitute one type of equation. And then we have our temperature changes. And as the temperature changes, that is a different type of calculation we'll have to look at. So first up, we will look at phase changes. So we have our heat of fusion. So that's the energy that must be put into a solid in order to melt it. Again, a reminder, breaking up those intermolecular forces. We also have our heat of vaporization, the energy that must be put into a liquid in order to vaporize it into a gas. And energy can be reported in a lot of different types of equations, or lots of different types of units. Energy can be kilojoules, joules, or calories. And the unit for the heat of fusion or the heat of vaporization could be in moles or grams. So when we do these calculations, pay attention to the unit you're being given, the unit you're being asked for. You may need to do a conversion or some dimensional analysis in order to solve the problem. In vapor pressure, we just want to refresh our memory on that. In a closed container, liquid evaporates and the gas collects above it. That vapor exerts a pressure, and that is our vapor pressure. And when vapor pressure equals atmospheric pressure, the liquid will boil. So liquids with weak intermolecular forces have low boiling points, high vapor pressures, and are called volatile liquids. Liquids with strong intermolecular forces have high boiling points, low vapor pressures, and are called non-volatile. So when we look at our vapor pressure graph, we can see our standard pressure, which is 101.3 kilopascals. There are a lot of other pressure units. This is just one of the more common ones. And we have things like chloroform on the left side, which is volatile with low intermolecular forces. And we have something with high intermolecular forces like ethanoic acid, which is non-volatile with that higher boiling point. Notice that, right, we have these curves to each of these substances that as we lower the pressure, the boiling point also is reduced. So with our phase changes, we have a relatively simple formula here. Q equals M delta H fusion, or we can do heat of vaporization. So we're just going to dive in here on a practice problem. If heat of fusion of iron 2 oxide is 33.2 kilojoules per mole, the amount of energy required to melt 5.6 moles of it is. So our equation, Q equals MHF. Q is the heat, or that energy. M is the amount of the substance. This is where your units have to agree with the unit that you've been given. So we've been given 33.2 kilojoules per mole, and the amount of energy required to melt 5.6 moles of it is. So because mole and mole will cancel out, we can use this problem as is. So now we just plug in the things that we need to know. Q equals 5.6 moles times 33.2 kilojoules per mole, and Q equals 186 kilojoules. And in our second example, if heat of vaporization of water is 2.22 kilojoules per gram, the amount of energy required to vaporize 10 moles of it is what? And again, we're using the very similar equation. Q equals M delta HV. Again, Q is the heat or energy, M is the amount, and then we have our heat of vaporization. Now, in this case, we have been given grams, and we have been given moles. And that's not going to work until we do a conversion. So we want to turn our moles into grams. And there we can use just a simple fence, 10 moles of water, and multiply by the molar mass, 18.01 grams per mole. And remember that just came from our periodic table. Oxygen is 16 grams, and there's one of them. We have 2 hydrogens, each at 1.01. Let me actually 18.02. So we end up with 180.2 grams. Now we can plug that into our formula. Q equals 180.2 grams times our 2.22 kilojoules per gram, and that will cancel out our grams, and then we can just put that into our calculator. 180.2 times 2.22 is 400 kilojoules of energy. For every substance, there is a energy input. There's a unique heat of fusion and heat of vaporization. Typically the heat of vaporization is a much higher number than the heat of fusion. So all those things are unique to the substance. And if you're looking at heat of fusion and heat of vaporization. But in general, when looking at these problems, you just want to make sure that you are matching up the units and converting if necessary. So what happens then if we have a temperature change? So if we have a temperature change, we are going to be looking at, so when we're at those plateaus on our energy diagram, we're going to be using heat of fusion or heat of vaporization. But when we have that positive slope that's indicating a temperature change, we have to account for that change in kinetic energy. And in this case, we're going to use a different example, a different equation, and that is going to be our specific heat capacity. And we're going to plug that into our formula. So specific heat capacity is the energy required to raise 1 gram of a substance 1 degree Celsius. And the units are joules per degree Celsius gram or joules per degree Kelvin and gram. It is easier to heat up a substance that has a lower specific heat capacity. And those things with a low specific heat, those are going to be your metals. Those are going to be things that are a good conductor because they can easily transfer the energy of heat along something like a copper wire. An everyday example, if you have ever used a spoon to stir like hot soup or coffee, and then you've put the spoon in your mouth and you've burned your tongue on that spoon, that's because the spoon heated very quickly in that hot substance. Alternatively, if you've ever used a metal spoon to scoop ice cream, and then the spoon kind of freezes over very quickly and gets very, very cold. And that is because something like a metal, being a good conductor, has a low specific heat. On the other hand, something like water has a high specific heat. And that is a property of water that you should have learned about back in your biology days. It's why something like a large body of water takes so long to heat, which is why water at a body of water for swimming is going to be warmest at the end of the summer when it's been able to absorb the energy of the sun the whole season. It's also why hurricane season is at the end of summer and into fall, because the source of energy for a hurricane is the warm water of the ocean. So it really needs that warm water that has built up, that thermal energy that is built up all summer long. So the formula is, sometimes I call it quick mad cat, but Q equals MC delta T, where Q is the heat or energy that is gained or lost. It typically just reporting it as a positive value is fine. Don't worry too much about if it's positive or negative in the end, because it's usually being phrased as how much energy is lost by the system or gained by the system. So you can just plug those numbers in. M is the mass of the substance in grams, so that gram will cancel out. C is the specific heat of the substance. Please be careful. C is the specific heat. Degree C is Celsius. And then delta T is that change in temperature. So that final temperature minus initial temperature. And just to give you an example of a specific heat value, here is water, 4.184 joules per gram Celsius. Okay, so let's look at a couple of examples here. Solid magnesium has a specific heat of 1.01. How much heat is given off by a 20-gram sample when it cools from 70 to 50 degrees Celsius? So Q equals MC delta T. We just want to plug in those numbers. Q is our energy. That is what we are solving for. Our M is 20 grams. C is that 1.01 joules per gram degrees Celsius. And our change in temperature is 20 degrees Celsius. Final temperature is 50 minus 70. Again, that's technically negative 20. But we're being asked how much heat is given off. And so really, we're just looking at that absolute value of energy. So grams in degrees Celsius will cool, joules will cancel, joules will end up being our unit. 20 times 1.02 times 20 ends up being 404, I believe. Yep, 404. And so all of these are really just Algebra 1 skills, a matter of plugging in numbers when you can. If you want to try this next problem, go ahead and give that a try here. You can pause the video and work it out. And when you plug that in, you should get an answer of 495 joules. It should be 0.9 is our specific heat, 55 grams is our mass, 10 is our change in temperature. So 55 times 0.9 times 10 and canceling the appropriate units. Okay, and we're going to pause here. In our video that this kind of covers that first half of thermodynamics. What is a heating curve? How do we do those basic energy calculations? We will talk in the future about some of those more advanced topics in our next video. Thanks for listening. Bye.